Okay. So, yeah, let me start with a few introductory remarks. This talk is a rather non-technical talk, as you may have guessed already from the title, which even sounds a little bit philosophical even. So it's also not that I will present big results here. It's more that I would like to share some thoughts with you about the connection between bounded rationality, which is an older branch of AI that was, I would say, most popular in the 1990s or so, yeah, when Bernd was just born, maybe, and related things such as rational meta-reasoning on the one side and AutoML on the other side. So this is a topic that we recently started to discuss a little bit about in my group, together with a couple of people, yeah, like those mentioned here: Jonas Hanselle, Felix Mohr, Alex Tornede, Marcel Weber, and a few others. We haven't been doing very much on the topic so far, but we find it quite interesting. What we have so far is a poster that we recently presented at the Automating Data Science workshop at the last ECML PKDD conference, and a connected, very short, actually, archive paper that you may have a look at if you find the topic interesting, which I hope will be the case. That would actually be great. That is also a bit the purpose of my presentation, to involve you in this discussion. And I thought for such a fall school, it might actually be perhaps not an uninteresting topic. So I have quite a generous time slot. I have seen 90 minutes, quite a lot of time. I can give the presentation first, and then we can discuss about, but I would also like to invite you to interact during the presentation, yeah, which is always a little bit nicer. Also to have some feedback, no clue to whom I'm currently speaking. And so please feel free to raise your hand, or just to speak up, to unmute yourself and speak up if you have any question or comment in between. Okay. So to start with, just as a very short reminder, many of you will know this view of artificial intelligence as, so to say, the science of rational agent design. Yeah, the goal of AI, one could say, is the design of rational agents, agents that sense the environment, yeah, with suitable sensors, etc., and then act and take actions and thereby change the environment, have an influence on the environment, and behave in a sense in a rational way. So they are doing, so to say, the right things or good things to achieve a certain purpose. And agents, the type of agents might be manifold, whatever you could think of. Could be a soccer playing robot, for example, could be a program playing a board game, but could also be an AutoML tool, for example. Yeah, we can also view an AutoML tool as such a kind of agent, and that will also be a view I am going to adopt during my presentation. So what does it mean actually to behave rationality, to behave rational? So the notion of rationality will be at the core of this presentation, and this is why I will start with making a few remarks on this notion and how to formalize it, how to realize it, how to define it. Then I will, this will be a main part of the talk, speak about these notions of bounded rationality and meta-reasoning that you may or may not be aware of. Perhaps you heard the term already at some point. And then I will explain how these notions relate to machine learning and automated machine learning. Finally, but this depends a little bit whether time permits or not, I will also make a connection to the field of preference learning, which personally I find very interesting. This is a topic that we have been working on a lot in my group during the past couple of years, and which I think could play an interesting role also in automated machine learning. So rationality, what is rationality and what is rational behavior? So when we speak about rational behavior, actually what we basically have in mind is the question how an agent should act and take decisions under uncertainty. This is an important point. When there is no uncertainty, we are essentially in the realm of optimization, and then there is little doubt about what is the right thing to do. Just seek for the optimum and essentially solve an optimization problem. But the question how to behave, how to take decisions becomes much more interesting if there is uncertainty involved, because then the answer, what is the right action to take, is no longer that clear. Such an agent could be, for example, a machine learning or an AutoML algorithm. I said that already, because such an algorithm is also taking decisions under uncertainty. Yeah? So, for example, if a machine learning algorithm solves the problem of induction and suggests a certain hypothesis or a predictive model, it is taking that decision under uncertainty because it doesn't know, of course, how that algorithm will really perform on a new data that it hasn't been trained on, so how it will generalize. Yeah. So this notion of rationality is actually not so new. It's a rather old notion, and it has been discussed a lot in philosophy. It's also at the core of economics and the behavioral science. Yeah, the Homo economicus, for example, yeah, is an idealized agent in economics that always takes the right, so to say, decisions. And various attempts have been made at formalizing this notion in the realm of decision theory. Of course, you can debate about what is the right thing to do or what actually rational behavior is. There is, however, a consensus that the so-called expected utility maximization principle is actually a quite rational principle, and this principle makes the following assumption. It basically assumes that a rationally behaving agent is acting in such a way that it maximizes expected utility. So more specifically, there exists a real valued utility function U, so that the agent in every situation chooses an action A star that maximizes expected utility, where the expected utility of an action AI is given by this expression here in the finite case. The infinite case, we have to replace the sum by an integral. So the utility of taking that action when the state of the environment or the state of nature, this notion is sometimes used, is Sj multiplied with the probability that this is really the case. So the probability of state Sj. There is uncertainty about Sj, and the principle assumes that this uncertainty by the agent is quantified in terms of a probability distribution. So this is the expected utility maximization principle. So why is this principle generally considered as a rational principle suitable to formalize this notion of rationality? One reason is that it can be justified in an axiomatic way. Yeah. So, for example, based on preferences over lotteries as primitives. So here you have a simple example. Imagine an agent can choose between three different actions, A1, A2, A3. The utility of taking that action depends on the state of nature, which could be S1, S2, S3. The probabilities of these states of nature are 0.5, 0.25, 0.25. So then essentially every act corresponds to a lottery. So for example, the first act A1 here corresponds to this lottery where you receive a reward of 100 with probability 1/2 and a reward of 0 also with probability 1/2. Yeah. For the second action, you receive a reward of 30 with probability 1 and so on. And now you can express preferences between these lotteries. You can say, okay, if I have the choice, for example, I would prefer the third lottery here, yeah, over the second and over the first, or whatever your preferences might be. In any case, if you obey certain properties, yeah, like these 5 here, for example, these axioms, which are all quite plausible in a sense. So for example, this one here, yeah, transitivity, if you prefer a lottery X to a lottery Y, and let me try to, yeah, if you prefer a lottery X to a lottery Y and a lottery Y to a lottery Z, then you should also prefer the lottery X to the lottery Z, etc. If you obey all these principles, which I don't want to discuss here in detail, then you can prove that you have, so to say, to follow the expected utility maximization principle. This is stated by this theorem here. So if these 5 axioms hold, or stated differently, these 5 axioms, A1 to A5, imply the expected utility maximization principle, which means that there exists a utility function U such that an action AI is preferred, weakly preferred to an action AK, if and only if its expected utility is greater equal the expected utility of AK. Yeah, and this utility function here is unique up to affine transformations. So it's essentially a unique utility function. Just a couple of remarks. These axioms that you have seen on the previous slide are basically due to von Neumann-Morgenstern. There are also other ways to justify the expected utility maximization principle. An even more general axiomatic system, for example, is due to Savage. He formalized this principle even without referring to objective probabilities in the form of lotteries. So he basically proceeds from even simpler primitives and does not even assume the existence of objective probabilities. Yeah. So he justifies what is called subjective expected utility theory. If you follow these axioms of Savage, then you can show that every decision maker behaves as if she had individual probabilistic beliefs on all the events in the form of a probability distribution, and once again applies this expected utility maximization principle. This expected utility maximization principle is very appealing from a normative point of view, especially due to these axiomatizations. But one has to admit that it's quite limited as a descriptive model. Yeah, there have been experiments in psychology showing that people actually do not, in general, behave as expected utility maximizers. They systematically violate actually this rule. And this is also why generalizations have been developed. There is non-additive expected utility theory, for example. There are theories such as prospect theory, etc., which all generalize expected utility theory to better describe how people actually behave in practice. So we may argue that this is actually not so important from an AI perspective, because we want to design agents that do not behave like people, but behave perhaps even better in a really rational way, in an optimal way, in a sense. So if we stick to this idea of expected utility maximization, and if the state and action spaces are finite, then we may represent our problem in the following way. We have a set of actions. We have a set of states of possible nature that we distinguish. We have a utility degree assigned to every state action pair, and we have a probability distribution on the set of states, then we may compute the expected utility for every action and choose the best one. Conceptually, this is very easy, but you can imagine that it's very difficult to put into practice, because you need all this information. So, for example, how do you know all the states of nature? How do you come up with a utility degree for every combination of act and state, etc., etc. And also, if the number of states you can, if the number of actions you can choose from and the number of states becomes large, you really need a lot of information. And this is why putting this principle into practice is often not really feasible. And this brings me to the notion of bounded rationality and meta reasoning. So it was a important insight by Herbert Simon that perfect rationality, in the sense we just discussed, is difficult and in general even impossible to achieve in practice, especially due to cognitive and computational limitations. So an agent, for example, a human, cannot really do expected utility maximization because it can the human cannot process all this information required and do all these computations. So therefore, as an alternative to this notion of perfect rationality, Simon proposed the concept of what he called bounded rationality. And in this regard, he introduced theories such as, for example, a satisficing, which very roughly speaking is the idea of finding solutions that are perhaps not optimal, but at least good enough, so to say, playing with what he calls an aspiration level, something you would like to achieve. There are works in a similar direction, for example, by Kahneman and Tversky, who investigate again how people are really taking decisions. So they are looking at decision making from a descriptive rather than a normative or prescriptive point of view in their heuristics and biases program, and also study how people systematically deviate from these norms of rational choice, like those dictated by this expected utility maximization principle, and propose things such as prospect theory I already mentioned. And likewise, for example, Gigerenzer, a psychologist, some of you may know, is working in Berlin, is an advocate of what he calls fast and frugal heuristics, which can be seen in a sense as a successor of Simon's notion of satisficing. So that aspect is, of course, this aspect of limited cognitive and computational capacities. This is, of course, also something that remains relevant from an AI perspective, because even if we have a computer or an intelligent agent taking decisions, computational resources are always limited in a sense. So our agent, whether it's an AutoML system or whatever, must act and take decisions under bounded resources. It does not have unlimited resources, unlimited capacity. And the interesting thing is that as soon as you have to take bounded resources into account, you solve the original problem, so to say, under constraints. And in a sense, you lose uniqueness of the solution. It's no longer exactly clear what is the right thing to do, because there are many compromises you could make. And more importantly, you have also now, because you have limited resources, you have to think about how you optimally make use of your resources. In other words, an agent acting under limited resources needs to decide how to decide, or think how to best take the decisions. So this thinking about how to decide is, again, a decision problem by itself. It's a decision problem, you could say, on a meta level, which again may cause costs and must again be solved under bounded resources. Yeah. So imagine, for example, you are writing an exam. Everyone knows that from experience. Then the actual problem, this is the problem on what is sometimes called the object level, yeah, in this field of bounded rationality. On the object level, you have a set of problems to solve in your exam. But typically before you start, you think about how you optimally approach the problem or solving the problem. So for instance, you have first a look at the entire exam to decide what problem you start with. Yeah. For every problem, you first, before you really try a solution, you think about what might be the best way of solving the problem. Even during the exam, you may have a strategy. Yeah, you may, for example, decide that if the solution to one problem takes too long, you stop and skip and proceed with the next problem because you don't want to lose too much time with a single problem, and so on and so on. And this type of reasoning is actually meta-level reasoning. It's meta-reasoning, reasoning on a meta level, in the sense of thinking about how to optimally solve the object level problem. Yeah, controlling, so to say, the reasoning strategy on the object level. Yeah, this is a picture you see quite often in this field of bounded rationality. We have a ground level where the agent is really doing something. The agent is really acting, for example, in game playing, it's doing a move on the board or so. You have a reasoning level, which is called the object level, where the actual decision problem, so to say, is solved. And then perhaps you have a meta level on which you think how to best solve the object level problem. So this point that the cost of decision-making should also be taken into account was made in the past by a couple of authors and researchers. So for example, Irving Good, he already in the 1970s, he coined a term called type 2 rationality. And what is actually sought in meta-reasoning is an optimal resource-bounded solution to what we can call an augmented problem consisting of the original problem on the object level and also the deliberation, so to say, on the meta level, the deliberation of how to optimally solve the actual problem on the object level. And you may immediately notice that this may theoretically, and this is a quite interesting point, lead to a kind of infinite regress, right? Because as I said, this problem on the meta level is again a decision problem. And now once again, you could say, you can think about how to optimally solve this decision problem. So you may add a meta-meta level if you want, and then a meta-meta-meta level, etc. This is certainly not what you want. So for example, in the writing exam example here, you should at some point really start solving the problems and not think for 2 hours about how to best do it, yeah, because then the exam is over and you haven't done anything. So clearly there is a need for finding a good compromise and cutting this potentially infinite regress at some point. So this notion of bounded rationality has also been discussed quite intensively in the field of AI. Especially, as I said, in the 1990s, but there is still work going on, and I have at least a little bit the feeling that it has also become, again, a little bit more popular in the last couple of years. There are a few more recent papers also appearing in that field, quite interesting papers, actually. And in AI, Stuart Russell, for example, makes a distinction between different types of rationality, which I briefly summarize here. So there is perfect rationality, first of all, and this is what we already talked about. Without going into the technical details, a perfectly rational agent is actually an agent realizing expected utility maximization. So in every situation, this agent takes the perfectly rational decision, namely the decision maximizing expected utility. The agent is acting in an environment E, has a utility function U, and this F here is the what is called the agent function. And this agent function prescribes simply actions that maximize the expected utility. So then there is what he calls calculative rationality. And this notion of rationality takes computational resources into account. It requires, so to say, that this function, this optimal agent function here, does not only exist, but is also computable in a computer science sense, roughly speaking. So mere existence is not enough. This function also needs to be computable, must be executable on a machine. Then there is meta-level rationality, and on this, in this regard, we make this distinction we just talked about between an object level and a meta level, of the problem-solving process. And what we seek, roughly speaking, is to maximize the overall performance, given the agent's object-level deliberation capabilities. This is still a relatively informal definition, so to say. And Russell, he especially advocated a notion he calls bounded rationality, which makes this a little bit more precise mathematically, and also poses, so to say, or defines the property in such a way that it's amenable, so to say, to optimization, so that you can at least theoretically show that an agent is behaving in a provably bounded optimal manner. So whereas this meta-level rationality here focuses on rationality of individual decisions, what bounded optimality is doing is reasoning over complete programs, which can be run on a machine, M, in an environment E. And what we are looking for is an agent that maximizes expected utility over all these possible programs that can be run on a given machine. So the bounded optimal program is a program that achieves the maximum expected utility when being run on this machine M in an environment E given a utility function U. So it achieves, so to say, the maximum expected utility, once again, within this restricted class of programs. This is important that this class of programs is restricted to make, so to say, the optimization problem well defined. What this notion of bounded optimality also assumes is a distribution over problems that need to be solved. At least it makes the assumption that such a distribution exists, even if it's not known to the agent. So let me illustrate these concepts a little bit to make them maybe more transparent, a little bit clearer. And let me use the example of multi-armed bandits for illustration. Probably most of you will be quite aware of the multi-armed bandit problem, and this also brings us immediately into the realm of machine learning. So in the multi-armed bandit problem, we have to take decisions sequentially. It's a sequential decision-making problem, and in every round we have the same set of options. So, for example, you can choose between 5 alternatives, A1 to A5. Every alternative, metaphorically, it's associated with a slot machine, so a single-arm bandit machine. Taking this action means you are pulling the arm and you receive a reward. And the reward is random. We make the assumption that behind every machine is a probability distribution generating these rewards. You can, there is a direct connection already to the AutoML problem, because, for instance, you may think of every single-armed bandit as an algorithm, for instance, support vector machine, random forest, and so on. And taking that action or pulling the respective arm could mean that you run the algorithm on a given data set with, for instance, a random hyperparameterization. You choose hyperparameters and random, and then you run the algorithm on the data set. And what you observe as a reward, for example, is the performance on some validation data set or so. More generally, as I said, we associate every arm with a probability distribution with a random variable, following a certain distribution. And if we pull the arm, we draw from that distribution. We generate a sample that is distributed according to the corresponding probability distribution. And then you can play different games with such a multi-arm bandit. So playing with a bandit means pulling arms, following a certain strategy. So for example, you start with the first arm, you observe a certain reward, then you try the third one, and the fourth one, etc. And what you can look at, for instance, is the cumulative reward. So you accumulate all the rewards you observe over time, you collect over time. And this is indeed one important task in the multi-arm bandit setting, to find a strategy that maximizes cumulative reward over time. But you might also be interested, for example, in not maximizing the cumulative reward, but the maximal reward you observe over time. So the max is here, for example, in the second row. Obviously, what is at the core of, so to say, playing this game successfully is finding a good balance between exploration and exploitation. On the one side, you should exploit the rewards that you have observed so far by choosing arms that seem to produce high rewards. For example, the fifth one here looks quite promising. But on the other side, you also need to exploit enough in order to do not miss opportunities. So for example, you should not completely give up on the fourth arm here only because you observed a relatively low reward once. Perhaps actually the fourth arm is quite good, and it was only by chance that in the first trial here, we generated a relatively low reward. So finding a good compromise between exploration and exploitation is really at the core of solving this multi-arm bandit problem in a successful way. There are many algorithms for doing that. So just to give you one example, the UCB algorithm, one of the best known algorithms in that field. This algorithm works as follows. It maintains a confidence interval for every arm, a confidence interval for the expected reward, the average reward that you produce by pulling that arm. And then in every round, it takes the arm which has the highest upper bound on this confidence interval. So here, for example, it would next pull the second arm. Looking at the highest upper bound is following a principle that is sometimes called optimism in the face of uncertainty principle. So the arms, so to say, are evaluated in an optimistic way. And this is the key for solving this or finding this good balance between exploration and exploitation. Then after pulling the arm, it updates the confidence interval, and in the next round, it chooses once again the arm with the highest upper bound, the fourth one in this example, and this goes on and on and on. Now let us look at a variant of this multi-arm bandit problem in order to illustrate these ideas of bounded rationality and so on. So imagine, for example, a variant of this multi-arm bandit problem in which we can only play for a fixed amount of time, for a fixed amount of time t. So imagine, for example, you are allowed to play in a casino for exactly 1 hour, Every arm may have a certain, pulling a certain arm, AI, may take a certain time ti, which may differ, for example, from arm to arm. Your goal is to maximize the performance till time t. So at the deadline, capital T, you would like to have your performance maximal. So for instance, to have accumulated the maximum amount of utility or money, for example, or perhaps the maximum reward you observed in the course of time till capital T. You have available a pool of multi-arm bandit algorithms, sampling strategies you can choose from. Let's call them A1 to A capital M. Might be greedy, epsilon greedy, for example, is a well-known strategy, UCB, Thompson sampling, etc., etc. Every algorithm, AI, we can assume also has hyperparameters, lambda I. And you are also allowed to mix and schedule different algorithms over the course of time. This is allowed. So, for example, you may decide that might be your strategy to start with greedy, with a hyperparameter of 0.1. Greedy always takes the arm with the currently highest average reward, so the one that seems to be best, with a probability 1 minus epsilon, and with the probability epsilon, it chooses any of the arms at random, uniformly at random. Then at a certain time point, you switch to UCB, and finally you play the arm which is currently the best one. You do not think anymore, but just play that arm till the end. That might be your strategy. And then you end at capital T, you end with a certain performance. Now, this, finding such a strategy here, of course, now calls for some sort of meta reasoning. At the meta level, at the object level, we are applying multi-arm bandit algorithms, which decide for us which arm will be pulled next. This is what a sampling strategy is doing. At the meta level now, we have to decide how to decide which arm to pull next. So we have to come up with a strategy of that kind here. Which algorithm do we apply? Or what should be the hyperparameters of that algorithm, etc. So rational meta reasoning now actually means that we take meta level decisions at every time point t in such a way that we maximize the expected performance at time capital T, at the deadline. And to take such a meta level decision at a certain time point t, the information we have at hand is given by the entire history we observed so far. It's called HT here. All the actions and rewards we have observed till time t. It's important to mention that such meta-level decision does not only influence the next, so to say, reward we observe, but also the future behavior of the multi-arm bandit algorithms, and therefore also the future utility of selecting them. Now we introduce, in a sense, a certain bias here for the utility of these strategies. And we could also say that it's in one way or the other, at this meta level, we also have to do exploration. We have to find a good trade-off between exploitation and exploration of these different sampling strategies we may choose from. So one question that, of course, arises immediately here is, what does actually this meta decision space look like? So what set of meta policies can the agent actually choose from? Now, this is not clear in this example, and this is also something that is in general often not very clear. So the space of potential meta policies, of course, is typically huge and not really mathematically well defined. So just to give you an example or a few examples of how such a meta policy may look like, we may, of course, decide to do no thinking at all. We could just pick a random arm at every point of time without thinking, or just the first arm or the cheapest arm, which needs the shortest amount of time, etc. And that might actually not be a bad strategy, because in particular, it maximizes the number of pulls you can make till time capital T. And this strategy might be especially good if the arms are roughly of the same quality, if they all produce more or less the same reward. Another strategy could be an explore then exploit strategy. You sample all the arms uniformly till a certain time point T0 to get an idea of what is the average reward and so on they produce and what is their runtime. And then from T0 on till the end, you choose the one that promises to produce the highest estimated expected improvement, till time capital T, in the remaining time you still have. Or you may solve the problem sequentially, and in the ith decision you take, you decide what algorithm, what multi-arm bandit algorithm you apply next, what with which hyperparameters, and for what amount of time delta T. This might be a meta-level decision, so to say, you take. There is also, of course, the possibility to adapt these meta policies through meta learning, to make them adaptive, hoping to improve them in the course of time. So, for example, this epsilon greedy strategy, it's really important to control the epsilon in a proper way. The epsilon should decrease in the course of time, so the amount of exploration should be reduced in the course of time, and exploitation should become higher. If you use such a strategy for deciding which epsilon value this greedy algorithm should take, this can be thought of something here at the meta level. At the object level, we apply the greedy algorithm with a parameter epsilon. It recommends an action to be taken, and this action is then taken at the ground level. This is called the ground level. This is the object level, and this would be a control strategy on the meta level. And this strategy to adapt the epsilon might, of course, again have parameters which you may try to learn. You may apply an algorithm, learn to adapt, which recommends parameterization of this strategy here. And this would be then a meta learning technique on a meta level, in a sense. Of course, you could also say you put everything together here and then call this algorithm, comprising all these different components. You give it a new name, you call it flex greedy or whatever, and this is just considered as a monolithic algorithm. The point I want to make here is that this distinction between object level, meta level, meta level, and so on, of course, always depends also a little bit on your point of view, right? And this also has to do with this notion of regress that I was mentioning before. So it depends always a little bit on the point of view, what you consider an algorithm on the object level and what you consider an algorithm on the meta level, etc. That is maybe something to keep in mind. So to achieve meta-level rationality, as I said, what we should try to do is to maximize the overall performance, given the agent's object-level deliberation capabilities. Here is a quote by Silberstein, for example. He put it like this. He said, given a particular object-level deliberation model, we look for the best possible way to control it, so as to optimize the actual ground-level performance of the agent. A key notion in this regard is what is called the value of computation. in meta-level rationality. And what this refers to is that computations on the meta level can be also perceived as actions. Yeah? Computations can be seen as actions on a meta level that may change the agent's informational state and possibly improve the decisions on the object level. So let me again use our example, our Bandit example, to illustrate this idea of this value of computation. So one simple strategy, for instance, is not to think at all and just pull an arm. So within a certain time interval, you may, for example, be able to pull a certain arm 6 times. Yeah, so you accumulate the reward over these 6 pulls of an arm. An alternative is to run a multi-arm bandit algorithm to decide which arm to pull. But then, of course, running this algorithm also needs time, and you will be able to pull less arms. So if you first run, for example, UCB to decide which arm to pull, then this takes more time. And within the same amount of time, for example, you might eventually only be able to pull 2 arms, not 6. And this strategy only pays off if eventually the multi-arm bandit algorithm is able to recommend a better arm. If this arm here is the same as that one, you do not gain anything. Actually, you lose, yeah, because you can pull the arm not as often as here, and the reward will be, or the expected reward will be the same. You only gain, and you have a positive value of computation, you only gain if this arm here is really better than that arm. And these two rewards here exceed the rewards of pulling that arm here 6 times. You may even go one step further and not only apply a multi-arm bandit algorithm, but an algorithm on a meta level that selects a multi-arm bandit algorithm. That is doing algorithm selection. For example, it says, oh, in this situation, I wouldn't apply UCB. I would perhaps better apply Thompson sampling. And then, and then you might, because this again takes time, you might, in the end, only be able to pull an arm once. And once again, the value of this meta computation here is only positive if it changes the action that is taken in the end in a positive way, so that pulling this arm here once is better in terms of accumulated reward than pulling, for example, this random arm 6 times. Yeah? So this is meant by this notion of value of computation. So if we view these computations, again, as actions or perhaps meta actions, then the task of meta reasoning can again be tackled by means of decision theory in a sense, yeah, because making computations is like taking an action. And therefore, in principle, selecting computations can again be based on expected utility theory. There are different ways to formalize meta reasoning as decision making. One simple architecture, let's say, or design pattern is shown here on the left. If we may assume that on the object level, we have something that is called an anytime algorithm, yeah, which we can interrupt, so to say, at any time, and which at any point of time produces a result. We can treat this anytime algorithm as a black box simply, and put on the meta level a controller that has access to this anytime algorithm and, yeah, controls it, as the name is suggesting, which turns it, for example, on and off, or which allocates certain resources to the anytime algorithm. This is a very simple connection between the meta and the object level. a more, let's say, or a tighter combination between object and meta level can be achieved, for instance, by combining the two levels into a joint MDP, a joint Markov decision process, considering a single state as a combination of an informational state and an environmental state. Yeah? And within such an MDP, or between such states, the agent may transition by either deciding to compute something and thereby changing its informational state, or taking an action and thereby changing the environmental state. This type of formalization of the problem would then also be amenable to applying, for example, reinforcement learning techniques. So here is a simple example of such a of this left setting here, the controller, so to say, where the goal is to find an optimal stopping time. If you control such an anytime algorithm, it runs in the course of time, and this controller here on the meta level may only be responsible to decide when to stop. So at every point of time, the question is whether you should continue deliberation or just stop and take an action. Yeah. So, for example, if you run an AutoML system, at every point of time, you may wonder whether you should just take your current favorite machine learning pipeline, for example, or whether you should keep on computing or searching for even better pipelines. Yeah? And this calls for finding an optimal compromise between the expected benefit and cost of taking an action. One way to tackle it, this was one way proposed in this literature on rational meta reasoning, is to refer to what is called the dynamic performance profile of an anytime algorithm. And such a dynamic performance profile specifies probabilities of this type, namely the probability to achieve a certain quality level Qj if the current quality level is Qi, and you continue running the algorithm for a further amount of time delta t. This is what is called a dynamic performance profile. So you currently have quality Qi, and if you continue your algorithm for a further time delta t, yeah, you have a certain probability of ending up with a certain quality degrees Qj. Yeah. So having such a performance profile, you can compute an expected value of computation in a myopic way. Yeah. What happens if you continue the algorithm for delta t? Yeah, with a certain probability, you produce a certain quality level Qj, and this is multiplied with a probability that this actually happens. And you have to subtract the utility of stopping, yeah, the current quality level that you already achieved. And then the difference between the two is the expected value of doing the computation. This is a myopic strategy. You can solve the problem optimally in a non-myopic way by applying dynamic programming. Yeah, just computing in a recursive way this value function here. What is the value of having a quality level Qi at time t? Yeah, the two decisions you can always take is to stop and to continue. If you stop, you have that, you end, so to say, with that quality level, and if you continue, you produce an expected quality after further time delta t. And you can prove, for example, this is one example where you can really prove that you come up with an optimal meta reasoning solution. A monitoring policy maximizing this value function here is a provably optimal stopping rule, provided certain technical assumptions are met, okay, which I don't detail here. In particular, the Markov property of the quality improvements. So here, maybe you have noticed we make a a Markov assumption, yeah, by just assuming that this improvement in quality only depends on the current quality QI and not on the complete history, so to say. And very importantly, monitoring has no cost. And this is, of course, typically not the case. Here it is the case that monitoring, in a sense, has no cost because monitoring can be pre-computed. We can compile a meta-reasoning strategy by computing this optimal stopping rule, so to say, offline. Yeah, but this is, of course, typically not the case. But under these simplified assumptions, we can really prove that this meta-level control strategy is doing an optimal thing, controlling the object level in an optimal way. So in a recent work, we have been doing something similar, I would say. That was even, by the way, before we started to talk about this connection to bounded rationality and so on. A paper that we recently published in the IEEE transactions on pattern analysis and machine intelligence, where we propose a method that predicts the runtime of machine learning pipelines in an AutoML context, yeah, with the idea or based on the observation that quite often it happens that you evaluate in an AutoML tool, you evaluate a promising machine learning pipeline, but the evaluation takes so long, the training and the evaluation of the pipeline takes so long that you run into a timeout. And then, of course, the value of computation is very low. Yeah, it's 0 or even negative because you don't you don't observe any result. And this is, of course, something you should avoid. And we propose a method to, before you start evaluating the pipeline, you predict the runtime to decide whether there is a good chance to make an observation, to produce a result before the timeout, or whether it's likely to run into a timeout. And this can be seen as a control strategy on a meta level, so to say. Now, obviously, this simple strategy can be further improved based on decision theoretic notions. Like, for example, we may ask ourselves not only this binary question, yeah, do we end before the timeout or do we run into a timeout? But we could also ask, what is the probability? What is the expected amount of time? With which probability do we produce which quality improvement and so on? And then reason in a more decision theoretic way about the expected utility of evaluating that pipeline. Okay. So, it's already relatively late, but I will quickly.
What do you think? How long do you still need, Eyke?
Yeah.
Like, I mean, I'm not putting any pressure on you. I mean, we have a 90-minute slot.
Yeah.
I don't know if you, for example, need like 10 minutes and then we have like 15 to 20 for discussion, Marius, that should be all right, right?
Yeah, 10 minutes is good. So
yeah, you have at least 10 minutes.
Yeah.
This is absolutely fine.
So the fourth part, as I said, it was optional. Let me now make a few remarks on the connection to machine learning and AutoML. And that will maybe take like 10 more minutes, and then we have enough time for discussion, okay? Yeah. Good. So now, what does this all, I mean, how does this relate to machine learning and automated machine learning? So let us first look at simple, so to say, standard machine learning, and in particular the standard setting of supervised machine learning. Where we have a certain set of training data, we apply a machine learning algorithm that does model induction, that produces a model or a hypothesis from that data by generalization, and then we apply that model to make predictions on new instances we haven't seen before. So this is a standard setting. It's summarized again here. What is the goal? in this setting of supervised learning, given an instance space X and an outcome space Y, and a hypothesis space H, the task of the learner, and a set of training data in the form of these tuples Xi, Yi. The task of the learner is to come up with a hypothesis that has minimal risk, minimal expected loss. The L here is our loss function that penalizes prediction, or should be H of Xi, sorry, Yi is switched here. And this is the task of the learning algorithm. So looking at this setting from this perspective of meta-level rationality or rational meta-reasoning, we can say that our agent, actually we have two agents in this scenario here. Our machine learning algorithm, let us call it the inducer, is an agent that learns a model on the object level. This is the actual machine learning problem we have to solve. An action of that agent is selecting a hypothesis given the data. So the agent function of that first agent is mapping data sets to hypotheses. This is what the agent function is doing of the first agent here. The second agent is the predictor on the ground level, which has an agent function here that maps instances to decisions or actions. This is what the second agent is doing, the predictor on the ground level. What does it mean that this predictor or this agent is behaving in a perfectly rational way? Well, in this machine learning setting, the perfectly rational agent, there is little doubt about this, is the pointwise Bayes predictor, which for every instance X, every query instance, takes the prediction which has the minimal expected loss. This exactly coincides with this notion of expected utility maximization. Here it's expected loss minimization. The Bayes predictor, so the Bayes predictor, which is the best hypothesis in our hypothesis space and which does not necessarily coincide with the pointwise Bayes predictor, this fits with this notion of bounded rationality, where we always assume that we have a finite set of programs or agent functions to choose from. Now, the question of rationality on the object level. So what does it mean that our inducer is behaving in a rational way? This is quite difficult to answer, right? Because an answer to that question would actually mean to answer the question, what is rational induction? What does it mean to solve the induction problem, going from data to general models in a rational way? To the best of my knowledge, there is no commonly agreed answer to that question. Interestingly, these ideas of boundedness and bounded rationality do not seem to play a very important role in standard machine learning. This is, of course, people are aware of that certain algorithms are more costly computationally, for example, than others. Training a decision tree can be done very quickly. Training a neural network takes more time, and so on. People are well aware of this, and they also quantify the complexity of machine learning algorithms as a function of the amount of training data and so on. But it's not really that in practice you try to find an optimal, so to say, compromise on a meta level or whatever. You just run an algorithm and it takes the time it needs. This becomes much more interesting in the realm of automated machine learning, where we are well aware of the fact that doing AutoML is very costly, and we cannot, let's say, explore the space of all machine learning pipelines exhaustively. This is why typically we run an AutoML tool with a certain timeout. So in the setting of AutoML, the learner, the AutoML tool, so to say, can now choose among a quite broad spectrum of inducers on the object level. Algorithms A SVM, neural networks, and so on, which come with a corresponding hypothesis space HA. A might be algorithms or even complex pipelines. Such algorithms have hyperparameters W that need to be set in one way or the other. So the AutoML learner has to basically propose a learning model in the form of such a triplet: a hypothesis space, learning algorithm A, and the hyperparameterization of that learning algorithm A. This is what the AutoML agent is doing on a meta level. So this learner is actually answering the question, which inducer is best for the given data set D. And on the object level, then this inducer is really run on the data to induce a hypothesis. So therefore, the goal of the AutoML agent is to find such an A star here, which eventually leads to a predictive model which has the lowest risk, the lowest expected loss. And now we have resource constraints. There is typically an upper time limit. There is also limited data that we can use for training and so on. So to solve this problem, we really need to do, or the AutoML agent really needs to engage in meta-level deliberation. This is now becoming very important. Now, comparing this AutoML problem with other problems that have typically been tackled in this realm of rational meta reasoning, we observe a couple of commonalities, but also a few differences. So first of all, it's not only the time that is a scarce resource here, but also the data, which is important in the realm of machine learning. The agent also has to think about, in a sense, how to optimally make use of the data, how to divide it, for example, into training, validation, test data, etc. The meta reasoning is actually, compared to the actual reasoning, which means the training of the final hypothesis, really costly and time consuming. It's much more time consuming than the actual reasoning. This is a little bit strange from the perspective of meta reasoning. Typically, the reasoning is the dominating part, and the meta reasoning is that part that takes less time. Sometimes it's even assumed that it takes no time at all in order to avoid this problem of infinite regress. In the case of AutoML, it's just the other way around. And therefore, one could even say that the meta level here is gaining in importance. And it may even suggest to engage in reasoning on a meta level, if you want. This has been done in various works in one way or the other in the recent past. So, for example, in one of the works we have been doing in my group, we have recently been looking into algorithm selection on a meta level, where we have algorithms, we have an algorithm selector, but then we have also an algorithm selector, so to say, which on a meta level decides what algorithm selector should optimally be taken to then take or decide for an algorithm to be run on the current data set. Also, maybe one interesting remark is that there is no clear-cut distinction between the meta and the object level in the case of AutoML. So strictly speaking, the meta reasoning problem should only involve simulations of trials, like, for example, when you apply a surrogate model in black box optimization. But if, for example, in AutoML, you evaluate a candidate pipeline, then what you are doing is you are really executing a real object. You are executing a real object level action, which also exhausts real resources. This is, strictly speaking, not an action on the meta level, and not pure liberation, so deliberation on the meta level. So it's something in between, you could say. It's in between pure deliberation and taking a real action. Especially, of course, it's not really a real action if the candidate you are evaluating is then discarded and not really used later on. So we could speak perhaps of something we may call a probing level, which exists in this setting of AutoML, where the agent can act like in the real world and test the effect of its actions, but without really actually causing any real effect. Now, this is a specific characteristic, I would say, of this AutoML setting. Okay, the fourth part I said is optional, so I will skip it in the interest of time. And wrap up. So to conclude, I hope at least I could give you an idea or convince you even that bounded rationality is quite an interesting branch to look at from an AutoML perspective. As I said, it's a relatively old branch of AI, but I think there are quite a number of very interesting ideas and concepts in this field of bounded rationality that might also be useful for AutoML. So, for example, things like the value of computation, this idea of a performance profile, of algorithm control, algorithm portfolios, this idea of satisficing in connection with what is called an aspiration level in Simon's notion of satisficing, and so on. They all do have natural counterparts in AutoML. So, for example, there is also this notion of information gain that has been used. The idea of learning curves and extrapolating learning curves is, of course, very closely connected to this idea of value of computation, etc. So there are already things that are done in the AutoML field and that naturally lend themselves to corresponding concepts in the realm of bounded rationality, but there is more, I would say, to exploit. By viewing AutoML as a specific type of rational meta-reasoning, that's what I wanted to say, we may open new perspectives. Like this idea, for example, of optimal stopping. I could imagine this could be practically interesting in AutoML, to decide what might be a good time point to stop deliberation and then train a model and deliver it as a result instead of using fixed timeouts. Yeah, for benchmarking, that's okay. Yeah, sure. But in practice, of course, such an optimal stopping rule might be an interesting alternative.
I mean, you said you wanted at least a little bit interaction. So we actually covered this in the introductory talk, and Marius and me have agreed many times that this is a super annoying open problem, how to do this optimally or rationally. I think maybe rationally is I think really the correct word here.
Yeah, absolutely. So yeah, in general, this suggests a decision theoretic approach to AutoML. And a really interesting question from my perspective is whether one could come up with any interesting theoretical results, perhaps to prove optimality of a meta-reasoning strategy, which will be very difficult, but perhaps possible under certain restrictive assumptions. So in other words, can you prove that your AutoML strategy is in a sense optimal among all possible AutoML strategies you could think of? And last but not least, the final point I wanted to make is then that one could, of course, looking at AutoML from this perspective of bounded rationality, even go beyond single AutoML tools or single problem-solving tasks, so to say, and ask ourselves whether AutoML research as a whole is done in a bounded optimal way. What I want to say is that AutoML, as we all know, is requiring a lot of computational resources. AutoML experiments are extremely costly, etc. And the question is whether we are using these resources in an optimal way, or whether we could perhaps do better. Do you really need the next AutoML experiment Is the value of computation, you are investing, is it really positive, and so on and so on. So on Thursday, I think there will be this discussion about green AutoML, and this goes exactly into that direction. All right, so here's a couple of references. Sorry for again taking quite a lot of time, but there is still a quarter of an hour or so, I think, left for discussion. So thank you very much. I will stop here.